So hello folks, we are going to talk today about diamond. So my name is Dr. Pradyumna Gupta. I have Rahul Ramamurti, President of Epidia Technologies. Synthetic diamond is something we want to talk about. These are not the one you get on jewelry. We are talking about something much more interesting to all these scientists, and that is diamond on semiconductor, uh, enabling quantum computing, energy, and even extreme environment like deep sea drilling. Right, there is a film, diamond film there, and outer space. So these are the things we are going to talk about with Rahul, and he has experience making these synthetic diamond. He does the consulting for that. So Rahul, welcome to the
Yeah,
show.
thank you.
So Rahul, first question. Okay, synthetic diamond. People hear about that and think, oh, lab grown diamond for jewelry. They don't think beyond jewelry. But that's not what we are talking about, right? What's
Right,
the real
right.
changing story behind synthetic diamonds?
Yeah, so diamonds are more than just fancy rocks. They are the ultimate semiconductor for high performance electronics. Uh, uh, they work under extreme conditions and for quantum tech. Recently, more in the last 10 years or so, for quantum tech applications. And synthetic diamonds are produced by two methods: high pressure, high temperature, and chemical vapor deposition. And diamond, of course, is a much superior material because of its extreme properties like high thermal conductivity, high hardness, and electronic properties like uh, high breakdown fields and for high temperature capability and
Hmm.
applications.
So when
So
that, yeah, go ahead.
So the big shift is still happening in semiconductor, power electronics, and quantum computing, where materials like silicon just keep up anymore.
So it is like, I think that is what gets me excited. Diamonds are moving beyond rings and into uh, AI processors, deep sea exploration and fusion energy, right? And
Right.
before we go there, CVD diamonds, uh, break it down for us. Like, how do you actually make a diamond in a lab? I'm very curious about it.
Right. So, chemical vapor deposition is the essence of the process. We use methane as a precursor gas and hydrogen as the carrier gas. And as we introduce hydrogen first in the reactor by after evacuating the chamber in the millitorr range to get rid of all the nitrogen so there's no impurities in the reactor, and then we strike a plasma by either or conventionally there are several methods. There are RF plasmas, microwave plasmas, hot filament methods. There are several ways to activate the hydrogen. The basic premise is that we want to get activated hydrogen to stabilize the diamond structure because hydrogen etches graphite and stabilizes diamond. So we want a lot of activated hydrogen. And so conventionally, hot filament and plasmas are the best way to go. Uh, so what happens in the reactor is hydrogen reacts with the methane in the feed gas
Hmm.
and reduces the methane to methyl radicals, which has carbon in the diamond form.
Hmm.
And that carbon in the diamond inserts into the diamond lattice or a seed crystal and continues to grow the lattice, just as you would in atomic level, like 3D printing, but at an atomic level,
Hmm. So it is like atom by atom you build. It is like
by atom or layer by layer. Yes,
it is like 3D printing, but at the atomic level.
That's
Uh,
correct. There are
so
several mechanisms, layer by layer or layer, uh, several islands merge together and form polycrystalline diamond, or layer by layer and form single crystal diamond. So
wow, that's wild actually. That's just amazing. Like 3D printing, but at atomic level.
that's
Uh,
right. That's right.
and you're telling me this same process lets you grow diamond that can outperform silicon in semiconductors.
That's right. Diamond is a wide bandgap semiconductor that can handle higher voltages, intrinsic heat, and faster switching speeds. Silicon is reaching its physical limits. Diamond based transistors can push it to the next generation of computing and power devices. Conventionally, uh, silicon based devices can only operate up to 150 or 200 C, but diamond based on its, because of its extreme properties, can operate at much higher temperatures, like beyond 500, 600 C. And also, diamond has high thermal conductivity, 5x that of copper, which means it's has really crazy cooling capabilities, like when you think of today's data centers. So that makes
Hmm.
it
Yeah, I
an
mean,
amazing material.
they need faster speeds and higher conductivity. Obviously, heat is a very big issue. Um,
Right,
so when silicon is running out of steam, I mean, everybody is talking about that. But and every few years, we hear that you know Moore's law is hitting its limit. There is now AI Moore's law. Uh,
right,
but how real it is that diamond replaces silicon? It feels very like sci-fi kind of stuff.
correct, correct. Yeah, yeah. Silicon has been around for more than 50 years. Uh, it won't replace diamond won't replace silicon overnight, but in high performance applications like in AI chips and power electronics, diamond is still looking like the next big leap. Think about power grids and electric vehicles.
Hmm.
Diamond transistors could make smaller, faster, and more efficient power converters. In quantum computing, nitrogen vacancy centers in diamond are being explored as stable qubits, which could make quantum computers much more practical. So that's where we are with diamond. Uh,
Hmm. So you're saying diamond could power the next gen AI processors, quantum computers, and you said like even the grid, right? That keeps our,
that's right. That's right.
the electricity grid you're talking about, right?
Right. Right. Power grids. Yes.
Hmm. Wow. So, is that like, correct? Like, just that these things could be actually become reality?
It might take. We are not there yet. There are power electronics components that are being made, like IGBTs, typically for such power applications, high power applications, because of diamonds' extreme properties, like operating at more than 10 kilovolts, and uh, in radiation heavy spaces, high heat, and even deep sea drilling. NASA is looking at diamonds for space electronics.
So why space electronics? Like, is it what is the advantage of diamond in space electronics?
Uh, so there are other materials that are still there in the market, like silicon carbide and gallium nitride. But the defense and other agencies are looking at putting diamond-based high electron mobility transistors
Hmm.
because of its high electron mobility and hole mobilities,
Hmm. So when in
and
the space,
capability to operate in harsh environments
hmm,
where in space applications.
So in space, is it because of the radiation? Like, I have heard
That's
about.
right. That's right. Radiation and harsh conditions as well as electronic. Uh, it's high power and high frequency capabilities to operate in microwave and
Hmm.
millimeter wave electronics.
Hmm. It's probably just fries, right? Silicon
Yeah.
is just
Right.
it
Right.
becomes real chip.
Correct. Correct. Correct.
Okay, I want to dive into quantum computing for a second, because I think that is where I think Diamond is, what I've heard is doing some next level stuff.
Correct.
Uh,
Correct.
what is happening there?
So basically, what we are creating is nitrogen vacancy centers in diamond. Diamond nitrogen has been known dopant in diamond for a long time, and by uh, irradiating the diamond with electrons or high energy particles, we create vacancies and then we anneal the material at 500, 600 C to move these vacancies to the nitrogen and then create nitrogen vacancies, kind of defects.
Hmm.
So these nitrogen vacancy defects act as qubits,
Hmm.
stable qubits, which is the essence of quantum computing,
Hmm.
uh, where other materials need to be cooled in order to operate as a quantum compute for quantum computing applications. Diamond can operate at room temperatures, which is the benefit, and you don't have to cool it,
Hmm.
super cool it. Or big players like IBM and Google are already experimenting with diamond-based quantum tech.
Hmm. So we are talking about future, a quantum future powered by diamond. That's nuts.
Yeah, exactly.
What about AI? What about AI?
Yeah, AI hardware generates massive heat, and thermal management is a huge problem.
Hmm.
So diamond, which is being a having high thermal conductivity and being a good heat spreader, could revolutionize cooling, making AI chips run more efficiently. Uh, yeah, we are seeing interest a lot in AI-based AI accelerators that use diamond for both computing and cooling.
Hmm. So, I mean, something was coming to my mind, like, if diamond is so powerful, why why are not we already using it in every semiconductor, power grid? What is the thing that is holding it back?
Still, growing high quality CVD diamond is an expensive process.
Hmm.
The
Hmm.
making at this point of the diamond growth cycle market, the market is still at growing 1 by 1 centimeter single crystal diamond, even though there are groups or teams, yeah, or groups or labs and even companies trying to get to 1 inch diameter diamond, single crystal diamond wafers.
Yeah, I've
And the
heard
claim
about like
is
3-inch wafer or something that has been.
that, yeah, that's the claim that they're making 4 inch diamond wafers. But that's a claim, and we are still trying to see if that's a uh, claim or it's really being evaluated.
Mm. So it's not then, sorry, it's not, just a second, yeah. So it's not a technical problem, that means it is a manufacturing scalability adoption problem, right? Because I think it will take some time also to replace the silicon, right? There is a inertia, there is. other things. But I mean, I think Dormant has not even crossed the first thing, which is basically the manufacturing something which can actually do some, we can show some viability with
That's correct. That's correct.
right?
It's there are viabilities to grow diamond 2 inch or even 4 inch, but it has not been proven. But there are methods to do that. Like conventionally, the way to grow large area diamond is either the mosaic method, where several it's called tiling or mosaic, where several single crystals of diamond are placed on a substrate, and or rather are placed on a substrate holder and merged, so or tiled, so they can eventually form a single crystal diamond of large diameter. Or another method is heteroepitaxial, which is growing diamond on foreign single crystals,
Mm-hmm.
like 2 inch or 4 inch single crystal sapphire, or um magnesium oxide.
Mm-hmm.
So these are other materials which have been explored, and these are all still in an evaluation stage in a lab, and have been proven to grow maybe 1 inch, I mean, square centimeter single crystal diamond heteropitaxially.
So, but the point remains that whichever method it is, even if there are a lot of advantage, and there is a, as you're saying, that there is a movement, major movement because of the power electronic, quantum computing, and AI hardware, is still, I think there are scale up and cost that are holding it back. Maybe it will go down, but it is not clear yet. So the advantages are so high, but probably the application is limited because
That's right.
of manufacturing things.
That's right. Scale up and cost is a major problem.
So
Yes.
my last question is this: what is the timeline here? Are we talking about 5 years, 10 years? What is your prediction?
Uh, I would say 5 years away for the next generation diamond. Uh, we are 5 years for diamond semiconductors. We already seeing first generation diamond transistors in development, like MOSFETs, uh, IGBTs, and the next 5 to 10 years, we'll see diamond power devices hitting mainstream markets.
Well,
So, and of course, in quantum applications and AI, it may be a little longer, even though there's exploration currently underway in several startups
hmm.
for diamond-based quantum devices.
So we are on the verge of diamond disrupting entire industries.
Exactly, exactly. Yes, it's not very far that we'll see this as a product conventionally in the market.
Great. That's a great conversation. Thanks a lot, Rahul. Synthetic diamond ain't just for the engagement ring. They are for AI quantum
Exactly.
power grids.
Sure.
So appreciate that you're coming here and opening our eyes on
You're
that.
right. Thanks a lot for the opportunity.